of referring expressions for human-robot interaction.
Hi everyone, my name is Mohit and I'm from NUS. My talk is about talking to robots. So in the future, we'll be living with autonomous butlers who will take care of our everyday needs like cooking and cleaning. So imagine if you could say, hey robot, stack the cups and put them in the shelf. Or hey robot, make me a fruit salad. Natural language provides a very powerful interface for humans to communicate with robots while also allowing robots to communicate back with humans. In this work, we take a look at a small subset of this natural language problem, which is to do with grounding referring expressions or locating objects from visual descriptions. And specifically, we take a look at three aspects of this problem. Firstly, how do we understand expressions like the blue soda can without explicitly defining object categories like apple, banana, or can? Also, how do we understand relationships like the blue can in the middle without explicitly defining templates like in the middle, on the left, on the right? And finally, in the case of ambiguity, we want the robot to ask smart questions, like, do you mean this blue can in the middle? And this allows us to solicit additional information from the user. To this end, we propose a unified framework called grounding by generation, which is broadly influenced by analysis by synthesis in cognitive science. Typically, visual grounding involves taking an image and an expression as input and outputting the location of the desired object. Visual generation involves taking an image and describing every object in the scene using visual attributes like color, shape, size, or spatial relationships. In our framework, we initially generate a set of descriptions for every object in the scene. And once the user provides an input, like find me the red can, we ground by finding the closest match to one of the generated expressions. In the case that the expression is ambiguous, we can use the same generated expression to ask a question, like, do you mean this left can? And this allows us to solicit additional information and communicate what the robot understands about the world. In implementation, this model is separated into two stages. In the first stage, we use a CNN LSTM architecture to generate a set of word probabilities representing a sentence for each object. And this is essentially a standard image captioning model from computer vision. Once the user provides an input like pick up the red can next to the teddy bear, we ground by clustering objects, which generated very similar expressions to the input expression. In the second stage, we examine all pairwise relationships of the chosen candidate objects. And again, using the grounding by generation principle, we generate a set of descriptions for each pair, which describe the spatial relationship for each pair. And then we ground by clustering pairs, which generated very similar expressions to the input expression. If we can choose a single pair with confidence, then our job is done. Otherwise, we use one of the generated expressions from the first stage or the second stage to ask questions. So we integrated this model with a Kinova Miko arm and an Amazon Echo Dot, and you're about to see a representative sample of the results. Note that all the objects you're about to see are part of the test set, which weren't seen during training.
Pick up the tennis ball.
It doesn't get confused with the other two balls.
Pick up the middle blue cup. Put it in the blue cup on the left. Pick up the left blue cups. Put it in the green cup on the far right. Pick up the water bottle.
It's ambiguous.
Do you mean this water bottle on the right?
No, the water bottle on the left. Pick up the stuffed animal.
Do you mean this teddy bear on the desk?
No.
Do you mean this stuffed animal with a black and yellow face?
Go ahead. Pick up the apple.
Do you mean this apple on the bottom right?
No, the apple on the top left. Pick up the soda can. Put it in my left hand.
So it also understands a bit about perspectives, like my left, my right. More details on this in the paper. We conducted a couple of user studies to evaluate our setup, and we found that our system is more accurate than a state-of-the-art baseline, and we're also faster in terms of disambiguation. I'd be happy to talk more in the poster session. Thank you.
Our third speaker is Valts Blukas.